In this video, we're going to go over the aldol addition reaction and also the aldol condensation reaction. So let's say if we have acetaldehyde and we react it with sodium hydroxide in water, the aldehyde molecule will react with itself to create an aldol addition product. As you can see, it consists of an aldehyde and an alcohol, and it makes sense that it's called an aldol product. So what we have here is a beta hydroxyaldehyde. The hydroxyl group, or the OH group, is on the beta carbon. But now let's go over the mechanism for this reaction. So in the first step, the hydroxide ion removes the alpha hydrogen, which is highlighted in blue. And so this is going to give us the enolate ion, which is resonance stabilized, but I'm just going to use this form of the enolate ion rather than the other resonance form. So now this enolate ion reacts with another aldehyde molecule. And so the nucleophilic carbon atom is going to attack the carbonyl carbon, causing that pi bond to break. And so the aldehyde functional group of the second molecule is turned into an alkoxide ion. And then this ion reacts with water, regenerating the hydroxide ion. And so that's the mechanism for the formation of the aldol addition product. Now, one thing I want to mention is that the aldol addition reaction is a reversible reaction. So it can go both ways. The reverse reaction is called the Retroaldol reaction. And let's write up a mechanism for the conversion of the aldol product into the original two aldehydes that made it. So the first thing that's going to happen is we're going to use a base to remove the hydrogen atom. And so we're going to get an alkoxide ion. Next, we're going to take a lone pair, reform the pi bond, and then this is going to cause the alpha beta bond to break. The electrons that hold the alpha and beta carbon will return back to the alpha carbon. And so now we have an enolate ion plus the other aldehyde molecule, which came from that part. Now the last thing that we need to do is we need to react the enolate ion with water. And so that's going to regenerate our hydroxide ion. And this will give us the original aldehyde molecule. And so that's the mechanism for the retroaldol reaction. Now once we have the aldol addition product, something else could happen. What do you think is going to happen if we heat this product? Now once we heat it, we're going to lose the alpha hydrogen and the OH group. So basically we lose water. And between the alpha and the beta carbon, a double bond will be formed. And so this is known as the alpha beta unsaturated aldehyde. And so this is also called the Aldol condensation reaction once we remove water. And as you can see, this aldehyde is stabilized due to conjugation. Now let's go over the mechanism for the formation of that product. So the first thing that's going to happen is that we need to remove the alpha hydrogen using the hydroxide ion. And so this will give us the enolate ion. Now, once we put the negative charge on the carbon atom, we can expel the hydroxyl group in the next step if we want to. And so this will give us our alpha beta unsaturated aldehyde. Now, there are other things that we could do with this mechanism. So once you're at this step, you can also do this as well. You can draw the resonance structure of the enolate ion. And then from this step, you can expel the leaving group, the hydroxyl group. Either case, you still get the same product. So it really doesn't matter how you do it. The end result is still the same. So that's the mechanism for the Aldol condensation reaction. Now let's work on an example problem. Feel free to pause the video and try this problem. Let's use acetone as our starting material, and let's react it with a base. Draw the aldol product and also the aldol condensation product, and show the mechanism throughout the process. So feel free to try that. So the first thing that's going to happen is we're going to use hydroxide to remove the alpha hydrogen. And so we're going to get the enolate ion. And then we're going to take that enolate ion and react it with another acetone molecule. So it's going to attack the carbonyl-carbon, and the pi bond is going to break. Now, this is going to be carbon 1, 2, 3. Carbon 3 connects to the carbonyl-carbon, so I'm going to call that 4, and this is 5. So I'm going to have a 5-carbon chain. So we have a ketone on carbon 2, and on carbon 4, we have an alkoxide, an oxygen with a negative charge. And also on carbon 4, we have a methyl group, which is here. Now, in the next step, this is going to react with water, regenerating the hydroxide ion. And so this is the aldol product. Now, once we have the aldol product, our next step is to deprotonate the alpha hydrogen to get the condensation product. So once we heat the solution, it's going to favor the formation of the condensation product. So first, let's put the negative charge on this carbon, and then let's form a pi bond, expelling the OH group. Now this methyl group, I'm going to push it facing up instead of facing in the downward direction. And now we have our alpha beta unsaturated ketone. So that's it for the mechanism where two acetone molecules react with each other. So here is the aldol addition product, and this is the aldol condensation product. Now let's work on this example. Let's say if we have a diketone, specifically a 1,5 diketone. So if this is carbon 1, the other ketone is on carbon 5. What's going to happen if we react it with a strong base? Now, what's going to happen is this molecule, it's going to become a ring when it undergoes the aldol addition reaction. And so this is going to be an intramolecular aldol reaction. Now, we can take this alpha hydrogen or this one. If the base goes for the white alpha hydrogen, we're going to get a 4-carbon ring, which is not stable. Now, if we take off the blue alpha hydrogen, we're going to get a 6-carbon ring, which is more stable. And so we're going to go for the blue alpha hydrogen. It really doesn't matter which particular ketone we choose to react because we have a symmetrical molecule. So we don't have to worry about getting a mixture of products in this example. So first, the base is going to take off the alpha hydrogen. And then the enolate ion will attack the other carbonyl group. And so it's going to close. Let's call this carbon 1, 2, 3, 4, 5, 6. So we're going to get a 6-carbon ring. Let me draw that again. And then let's make carbon 2, let's put it on top. So this is carbon 2, let's say that's 1, this is 3, 4, 5, and this is 6. On carbon 6, we have a single bond to an oxygen with a negative charge. And also, there's a methyl group attached to carbon 6. So in the next step, we need to protonate the alkoxide ion. And so now we have the aldol addition product. Now the next thing that we need to do is that we need to remove the alpha hydrogen. So we need to use hydroxide to form the enolate ion. Now in the next step, we can eliminate the hydroxyl group. So now we have our final product, which looks like this. So we have a CH3 here on the beta carbon and a ketone at the top and a double bond between the alpha and the beta carbon. And so this is the product. Now let's talk about the cross-aldol reaction. So let's say if we have a 2-carbon aldehyde and we wish to react it with a 3-carbon aldehyde. What products can form in this reaction? Let's call this reactant A and reactant B. So A can react with B can react with A can react with itself, and B can react with itself. And so we can get a mixture of 4 products, not including stereoisomers. Now, if you do include stereoisomers, you can get up to 8 products. Because A and B, you can get the cis and a trans isomer. Or, and sometimes, it could be just the E and Z isomer. So keep that in mind. So you can get 4 different products, but 8 different stereoisomers. Now let's start with this example. So we're not going to do the mechanism. So the way I set it up, A is going to attack B. So the alpha carbon of A will attack the carbonyl carbon of B. Therefore, when you count the longest chain, once you get to the alpha carbon of A, jump to the carbonyl carbon of B. And so we're going to have a 5-carbon chain in this reaction. Carbon 3, where the carbonyl group was attacked, that's going to turn into an OH. And once we heat it, we're going to remove water between the alpha carbon and the beta carbon. So we're going to get a double bond in that region. So this is the final condensation product. Right now, this is the trans isomer. And so if we want to, we can also draw the cis isomer. But typically, this is going to be the minor product. So if I draw just one product, just know that you can get the other isomer, the cis and trans isomer or the E and Z isomer. Now let's take the 3-carbon aldehyde and let's react it with the 2-carbon aldehyde. So in this case, this is reactant B reacting with A. So we know that the alpha carbon of B will attack the carbonyl carbon of A. So therefore, this is going to be 1, 2, 3, and 4. So the longest chain will be a 4-carbon chain. On carbon 3, we're going to get the OH, and on carbon 2, we have a methyl group, which I'm going to put here. And so now, once we heat it, we're going to remove water from the alpha and the beta carbon. So we're going to put a double bond between the alpha and the beta carbon. And so this is going to be, the OH group shouldn't be there anymore. This is going to be the final product. Now the other isomer, we can draw it like this. So right now, the hydrogen is close to the carbonyl oxygen. In this case, we're going to put the methyl close to it. So in this example, this is the highest priority on the left side. This is the highest priority on the right side. So this is the Z isomer. And then these two are the highest priority. So this is the E isomer. So you can get E and Z isomers in this example. Now for the next example, we're going to mix reactant A with itself. And we've seen this example. That's where the 2 carbon aldehydes are reacting with each other. This is called acetaldehyde. And so this is going to be carbon 1, 2, 3, and 4. And so on carbon 3, we're going to have the OH group. And then once we heat it, we're going to put a double bond between the alpha and the beta carbon. So right now, this is the trans isomer. And so we can also get the cis isomer. Now, let's mix reactant B with B. In this case, it's going to be the 3-carbon aldehyde, propanol, with itself. So the alpha carbon, which is carbon 2, will attack the carbonyl carbon, carbon 3. So the longest chain will have 5 carbons. So we're going to have an OH on carbon 3, and then we can see there's a methyl on carbon 2. And then we need to heat it. So just like before, we're going to put a double bond between the alpha and the beta carbon, and then the OH group is going to leave as water, as well as the alpha hydrogen. And so this is the E isomer, and so the other product will be the Z isomer. And so that's it for the cross-aldol reaction. So those are the different products that you can get between ethanol and propanol when they react with each other under basic conditions. Now sometimes you might be given the product of the Aldol condensation reaction, and you need to determine the original aldehydes or ketones that make up that product. How can you do so? The first thing you need to do is identify the alpha and the beta carbon with respect to this ketone. And then you need to break the bond between the alpha and the beta carbon atoms. And so on the left side, we can see that we have acetone. On the right side, we have 3 carbons that look like this. Now on the beta carbon, you want to keep the double bond and then just add an oxygen. So the 2 reactants in this case are 2 acetone molecules. Now let's look at some other examples. Let's start with this one, a familiar example. This was the first aldol condensation reaction that we did. So here is the alpha and the beta carbon, and so this is going to be the bond that we're going to break. So on the left side, we have a 2-carbon aldehyde. Now on the right side, let's draw what we see here. So there's 2 carbons, and here is the double bond, and just add the oxygen to it. So this is the reaction between 2 carbon aldehydes. Now here's another example that we also covered in this video. Go ahead and try this one. Determine the reactants of this reaction. So identify the alpha and the beta carbon atoms, and then break the bond between them. So on the left side, we have, if you count it, it's going to be a 3-carbon aldehyde, which looks like that. And on the right side, all we have is 2 carbons, 1 and 2. So we have a 3-carbon aldehyde reacting with a 2-carbon aldehyde. That led us to get this product. Now let's work on one more example. So let's say we have a cyclic product. Go ahead and determine the aldehydes and the ketones that made this product. So once again, identify the alpha and the beta carbon atoms, and then break the bond between them. Now on the beta carbon, we're going to put the double bond O here. And so this is the same if we draw it this way. So we have 7 carbon atoms. So 2, 3, 4, 5, 6, 7. And there's a ketone on carbons 2 and 6. And so that's how you can determine the original reactant if you're given the product of an aldol condensation reaction.